begin with a word of prayer? I take my coat off here. I bet you. Sit down there, buddy. Yeah. All right. Dear Heavenly Father, we thank you for this morning. I just ask you to help us use this time wisely, Lord. In your name I pray. Amen. What was that? Minions? Sounds like Minions. All right. I'll get my laptop out here so I can know which questions you guys are asking about. You can go ahead and ask though. Well, 110? All right. Let's see here. Mission 7, right? Suppose V is a finite dimensional vector space and V is the direct sum of W1 and W2. Does it follow that the annihilator of W1, the direct sum of the annihilator of W2 is V star? Prove or disprove? All right, so we're given that V is the direct sum of W1 and W2. You can assume that these are finite dimensional. It might still be true in the case it's infinite dimensional, but I'm fine with you guys assuming it's finite dimensional. And the question is true or false? Is the dual to V the direct sum of the annihilator of W1 and the annihilator of W2? So I guess the first question you might have is, what's an annihilator, right? So what does this mean, annihilator of W1? So what this would mean would be, say, alpha, excuse me, alpha from V to the field, right? Such that alpha of x is equal to 0 for all x in W1. So, do you want to take off your coat, little man? Take off your coat? There we go. Take this baby. There we go. So that's the definition of the annihilator. It's a set of all, quote-unquote, dual vectors, right, which are just linear transformations of the vector space to the field that make all of W1 go to 0, right? And, doesn't need the hat now. Thanks, buddy. And likewise for W2, right? So what do you guys think? How should we proceed here? My intuition here is that it's true. And the reason for that is that the annihilator of a space is like complementary in dimension. For example, like here's my intuition for this. If we were to look at, say, W is the span of 1, 1, 1 in R3, then W dual, well, the annihilator of W, rather, would be, like alpha alpha of x, alpha such that R3 goes to R, and alpha of 1, 1, 1 equal to 0, right? I'm not going over the proof right now. I'm showing you why I know that we should try to prove it's true. So a specific example of an annihilator would be this. If I take, that's like the z-axis, right? What's the annihilator of the z-axis? Hey, little buddy. Want me to take your baby? Think. Put him up here. Put him there. Let me put him there for you. Is that good? That's good, right? Yeah, he likes that. So this one, I mean, this is a linear transformation. I'm saying it's linear, so this is basically in the only condition. I mean, so what kind of matrix do you want? I mean, alpha, you can write, in this case, alpha of x is equal to, like, some matrix times x1, x2, x3, right? And it has to be a 1 by 3, right? That's the matrix of a linear mapping from R3 to R1. It would be a 1 by 3. So basically, you're just looking for ABC to fix alpha. Oops. You okay, buddy? I'm sorry. I hit you with my microphone. Oh, little buddy. There we go. So, this is AX1, BX2 plus CX3. That's like, this is a generic formula for a dual vector. This is just a generic formula for a dual vector of R3, period, right? When we talked about this before, I mentioned you can form any dual vector to like Rn by the dot product of a vector, right? So like as a specific, I think I called it alpha sub w or something here. Anyway, my point is, in this case, there's only one condition on alpha, which is that alpha of 1, 1, 1 equal to 0, right? Which would say that A1, that would say that A plus B plus C is equal to 0, right? Therefore, the annihilator of W is essentially, let's see here. Sorry, this is taking me longer than I wanted. So another way, alpha is A e upper 1 plus B e upper 2 plus C e upper 3, where E upper j with EI is Kronecker delta JI, right? The dual basis to the standard basis. And the A, B, and C are not free for alpha in the annihilator of W. They face this condition, right? So I can actually write alpha as equal to, say, like AE1 plus BE2. And what's C? Well, we can make C minus A minus B, right? So it's taking me forever, but getting to the point here, this is A times E1 minus E upper 1 minus E upper 3 plus B times E upper 2 minus E upper 3, right? And so, by the way, this and this are linearly independent, right? So therefore, the annihilator of W here is the span of E1 minus E3, E2 minus E3. So what I'm trying to get at here is that if W is one-dimensional in a three-dimensional backdrop, right, then the annihilator of W is 3 minus 1, which is two-dimensional. So when I look at W1, direct sum W2 being all of V, it says to me that like the annihilator of W1. So let's suppose that this is M1 dimensional, and suppose that that is M2 dimensional, and that n is equal to m1 plus m2, right? Then my expectation is that the annihilator of W1 is what dimensional? I kind of expect that the annihilator W1 is n minus m1 equals to m2 dimensional. I expect that the annihilator W2 is n minus m2, which of course is m1 dimensional. In other words, if I was to calculate the, what would give you a direct sum with W in my specific example? If we put W2 equal to span of what? So this is W1, basically. I mean, W, rather. Anything will work here as long as W2 has two vectors which are not collinear, or the sum of which is not collinear with the z-axis. So, for example, the xy plane works nice for W2 in my thought process here. You know. That's a potential orthogonal complement. And what would happen if I looked at the annihilator of W2? What would it be? I'm pretty sure it would be the span of E3. Because E3 only is non-zero when it hits E lower 3. And so it automatically kills these two vectors. All right, well, this is not a proof. I'm just trying to give you some sense of like why I think this is true. So how should we prove it? I hope I've justified to you why I think it's true. How do we prove that's true? What does it take to show that V dual is the direct sum of the annihilator of W1 and W2? Or more generally, how do you show that a vector space is the direct sum of two subspaces? Like, what are strategies? Remember theorem 6.7.8 has sort of a list of 5 equivalent strategies, right? Like, any one of those things could appear as the definition. I oftentimes find it helpful to show the intersection of them as 0 as kind of that's usually a fairly simple thing to do in the big scheme of what's involved here. This one, I kind of think I can do a basis kind of argument here is one way to do it, right? I may have to argue from a basis calculation here. Let me just take a glance at my solution, make sure I'm not missing something. Yeah, my solution's based on looking at a basis and following it through. So a sketch of the solution is this. Let beta equal to beta 1 union beta 2 be basis for V, all right? Equal to W1 direct sum W2, all right? So the problem breaks down like this. Let's let beta 1 equal to, let's say, V1 comma I. I equals 1 to m1 union v2 comma j equals 1 to m2. Oh, I'm sorry, that was, the first one was beta 1, and the second one I wrote here was what? That was beta 2. So I'm saying find a basis for W1, find a basis for W2, and then study how the dual basis behaves, right? So like beta dual would generically be speaking, it would be V sub, let's say, K, KL, excuse me, V upper KL, K equals to, it's a little bit complicated here, K equals to 0, or K equals to 1 or 2, right? I don't know, I can't even express this easily. So 1 less than or equal to, how can I say this? 1 equals to K means that 1 is less than or equal to L is less than or equal to M1. Or 2 equals to K and 1 less than or equal to L less than or equal to M2. I mean, these are the two choices with my notation. Maybe, I mean, I don't know, we could. Do you guys like the double indices? We could instead use 2 different letters if that would be easier. I mean, the alternative notational scheme here would be something like, well, anyway, I've already done this, so let's stick with it. So this, you could see, is the union of 2 things, right? There's like, well, you guys, your choice. What do you want to call the ones that are like the first case? My question is, do you think, well, words. My claim is essentially this. This case gives W, well not, yeah, okay, so this gives W 1 dual. And this one gives, and I probably should put some quotes on that, W2 dual. The reason I got to put quotes is like, the dual for subspaces would technically be mappings from the subspace to the field. But to be picky, these are subsets of V dual, so the domain is all of V, which wouldn't quite match the like logical notation for W1, W2 dual. But that's the case. So what I'm trying to say here is that these particular choices give me dual vectors which can be non-trivial. The outputs can be non-trivial on W1, whereas these ones give me outputs which could be non-trivial on W2 for inputs that are from W2. So if you think about that, if you're looking for a basis for the annihilator of W1 and the annihilator of W2, that suggests that this may be basis. If you want the annihilator of W1 is supposed to kill everything in W1, right? Which means it's only non-trivial in W2. It stands to reason that this must be the basis for the annihilator of W1. And the ones of these that correspond to this case must be giving us the basis for, oh, what is, you want me to put him back up here? He should be here? Is that good? Like that? Like that? It's kind of, he wants to jump. Sorry. You know. Here, take a nap. Is that better? Uh-oh. Yeah. This should be basis for W. The annihilator of W2. Oh no! Pick him up, buddy. So, I'm claiming that you can show that the annihilator of W2 is the span of V1, comma I, such that 1 less than or equal to I less than or equal to M2. And you can show that the annihilator for W1 is that, and that's supposed to be V upper, I'm sorry guys, V1 upper 1I. And over here the span of V2, J, such that 1 less than or equal to J less than or equal to M1. Maybe the critical calculation here is, I mean, that's essentially, this is in tune with my initial, whatchamacallit there. This room is really cramped, isn't it? I should go searching for another possibility for us in this time. The only thing that's forcing us to end it at 9:05 is the fact there's a lab in here at 9:15, usually. So you okay, buddy? You all right? Can you come up? Man. So as you think about the way this works, V1I with V2J is 0. V1I with V1J is equal to Kronecker delta Ij. V2I with V2J is Kronecker delta Ij. And V2I with V1J is equal to 0. That's how the dual basis is defined in this notation. The dual basis is the basis for the dual space that is only non-zero when it hits the basis which is dual to it in the original vector space. So these should guide the calculation, but you can essentially prove that the annihilator of W1 is built from the span of the things which are dual to the W2 basis, and the annihilator of W1 is built from the span of the things that are dual to the W1 basis. So they're complementary in dimension, but since they're both complementary, it means that the direct sum of them has to be everything. So if you could prove this, you don't even need to look at the intersection because counting finishes it for you, right? No. This is, why don't we have to look at the intersections? Because the union, if you prove what I'm saying here, if you prove that that's a basis for that and that's a basis for that, then that means when you put them together, you have a basis for the whole dual space. But we won't know one of the 5 equivalent conditions is if you can concatenate bases for the subspaces, put them together and get a basis for the whole space, that serves to prove that the subspaces in question form a direct sum. Here the subspaces I'm talking about are annihilator of W1 and annihilator of W2. That's a sketch, though. It took me about a page to write it out. You guys have other questions? Let me try to redeem the day by answering something that I can answer in more detail. Pew, 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 pew. 112. So you're supposed to show that the symmetric matrices are an invariant subspace and that the antisymmetric matrices are in the kernel of T, and then to look at the direct sum decomposition of the mapping if we choose a basis which respects the decomposition into symmetric and antisymmetric. So the map, I got to be careful. If I'm not careful, I'm going to smush them into the wall when I turn around. So rather than working, if I don't want to work this problem directly. So let me just change the problem ever so slightly so I can show you something. Was it 112? So if we look at a very similar mapping, so I'm going to change the plus to a minus. If I change the plus to a minus, it's a very similar problem, but the roles of A sub n and S sub n interchange. What's the kernel of T look like? In other words, the kernel in this case is literally symmetric n by n matrices, right? Which I've called, I'm trying to use a like this kind of S for it, generically speaking in here. The reason being in 421 we use capital S lower n for a different thing. So I don't want to like, because you guys will tend to think a notation is reserved if it's introduced like that. So just for the sake of not corrupting your intuition for 421, I try to use a script S here when I remember. Okay, so are we on board? Is that an invariant subspace? What's it mean for it to be an invariant subspace? What makes W an invariant subspace? W, a subspace of V, with T of W, a subset of W, means that W makes W so-called T invariant. Right? That's the definition. And I would remind you that we proved that the kernel of any polynomial in T is an invariant subspace. So certainly the kernel is an invariant subspace as a specific case of that thing we proved in class, but we could also just prove it, you know. So let A be in the kernel of T. Consider T of TA, T of TA, right? Then that's T of 0, which is equal to 0. Therefore, T of A is in the kernel of T. And what's that say? That says that the image of the kernel is a subset of the kernel, right? Anything in the, if we take T of something in the kernel, we get something in the kernel, which is to say it's an invariant subspace, right? Hey, Benjamin. Give me your duck lips, huh? All right. And were we supposed to, in part A and B, are we supposed to show they're both invariant subspaces?
Well, the first one is show it's an invariant subspace, and part B says it's
Contained in the... Oh, it's okay. I got it. Ah. So I should probably show here AN is an invariant subspace as well, right? So I think that, if we let's say, let's use a different letter to make it look different. Let B be in AN. A, meaning what? And I'm trying to use a slightly different looking A when I remember. A transpose is equal to minus A, right? So then consider T of B, right? Duh. I just said B and then I gave you a condition on A. Dumb. So B B be an antisymmetric matrix, if we look at T of B, right, I'm going to try to prove that the antisymmetric matrices are an invariant subspace for this linear transformation. In your homework problem, actually it's the case that both the AN and the SN are invariant subspaces. But if you show that one of them is the subspace of the kernel, that means that not only is it an invariant subspace, that means that the block that corresponds to that part of the matrix, part of the transformation, will be 0. Right? Things that are a subset of the kernel are things that map to 0. Okay, anyway, so T of B, what does it take, if I want to test whether or not T of B is in AN or not, what do I have to check? What does it take to be in the club, so to speak? What's the definition of AN? It's that when we take the transpose of it, right, we get back minus what we started with, right? So how do you actually check that here? Well, what's the definition of my T? B minus B transpose, right? Which is, of course, B transpose minus B, transpose, which of course is B again. And that is what? That is minus parentheses, B minus B transpose, right? Which is minus T of B. So that shows us that T of the antisymmetric matrices is a subset of the antisymmetric matrices. Which is what we need to prove that antisymmetric matrices are an invariant subspace, right? Now, we have previously shown, what's the situation here then? For this mapping, we have T is a mapping from the symmetric matrices direct sum, the antisymmetric matrices, to the symmetric matrices direct sum, the antisymmetric matrices, right? How do I know that all n by n matrices are the direct sum of Sn and An? Well, we've proved this before, right? I mean, this is something that we know. Of course, if I have a problem on like the next test or the final that asks you to prove this, I'm not looking for you to tell me, oh, we already know this. Like, I'd like to actually see why this is true. There are any number of ways to prove this. Yes, Benjamin. But it is true. And so, if we look at our n by n with basis beta, say the basis for Sn, union with the basis for An, right? Which is really, I'm gonna call that BS and BA, just to not write quite so much, yeah. And it's probably still too much, but anyway. So what would the mapping TSN, right, is a mapping from Sn to Sn, right? And the T sub An is a special mapping we define from An to An. What are those given by here? Tsn of A equals to what? So T sub Sn of A we define going these. Remember T sub W. If this is the case, then you can define T sub W, which is a new mapping that goes from W to W, where T sub W of X is just equal to T of X for X and W. So I'm using this definition, which is only available. That definition is only available if our subspace is an invariant subspace. If it's not an invariant subspace, I can't logically define these mappings, but here I can. So what's T sub Sn of A? What did we prove? If we're in the That just maps to 0, right? Because anything in the symmetric part maps to 0 under T. How about the part that's the antisymmetric part? Well, that maps to A, what was the definite? A minus A transpose, right? But what's that equal to here? Not 0 this time. What's A transpose is equal to what? A transpose is equal to, not A transpose, but minus A, because this is antisymmetric. So in other words, this is 2 times A. So actually, the mapping restricts to 2 times the identity mapping on AN. All right? Yeah.
So, I don't know if I can talk about like this problem, like that we're actually doing. So it's A plus.
A plus.
So would it be 0 or?
A plus, the roles of Sn and An are dual. Like it's 0 on An, and it's twice the identity on Sn.
Oh, okay.
But it's
So it's flipped.
yeah, it's flipped for the homework problem. But for this problem, if we look at the matrix of T beta beta, right, then by the general theorem, it's the matrix of Sn with respect to the, beta S matrix basis. And then there's a 0, the matrix of the AN restriction to the BA matrix, BA basis. And so what you've got here actually is 0, 0, 0, and 2 times the identity. In other words, you've got 0 direct sum 2 times the identity matrix. Now, what's the size of the identity? Let's say D. And let's say that let me call that D2. Say that's the D1. What's the dimension? What's D1 equal to? What's D2 equal to? D1 would be the dimension of Sn here. D2 would be the dimension of An in terms of like the size of these things. The last test, one of the problems that nobody solved because, the test was hard, and this was the hardest part thing, and nobody quite got to. It's fine. But I shared with you guys that this is 1/2 n squared plus n, whereas the dimension of An is 1/2 n squared minus n. So, this is not necessary for the problem. I forget, it depends on how I asked it. Find the symmetric. Well, the best answer would involve this, because that would tell you how big the blocks are, right? So the lower block is it's the D2 by D2. D2 by D2, yeah? Where D2 is 1/2 of n squared minus n. And the 0, the upper left block, is bigger. It's the size of the symmetric matrices. It's 1/2 n squared plus n. No, you don't want to unplug those. It's no fun. It's not fun. It's not fun. You won't do that. No. Here, have a gun. No? You can shoot them. You don't want to shoot them? What if I gave you... Here, I have a better gun. Just a second here. Do. There you go. Now you're properly armed. All right. Go get them. Go show them who's boss. Yeah, you do it. Uh-oh. Do you want me to pull that for you? Yeah. Okay. No, don't shoot me. Well, he doesn't usually know how to do that. That's new.
These children do things that
Ah, children do learn, that's true. Okay, so the reason there is a harder and more detailed way of doing this problem is to actually find the bases for this and sort through it in gory detail. The reason I showed you the solution to the corresponding problem in this way is to illustrate you don't actually need to do that, right? If you can see how the mapping works on the subspace in terms of a generic subspace element, you don't actually have to go to the nuts and bolts of the basis to figure out what goes in the block, right? And yet, you need to know how many things that are in the matrix are in the basis in order to figure out how big the block is that's true. So, anyway, ha! Wow, you got me! How dare you! How dare you! Do you guys have? I'll try to give you a sketch to an answer to one more. I think that's all I have time for at the moment. Let's talk about 116. Problem 116 is to calculate a to the n. And what else is going on in that problem?
What else are you finding?
Yeah, like, I mean, what is the preamble to? That's the tail end of the problem.
Yeah.
The end of the problem says, hey, calculate it at the end, like an afterthought, you know? And the reason that's an afterthought there, already at this point in the problem, you have calculated the eigenvalues and the corresponding eigenvectors, right? Oh! Ah! Yes. So something I have derived in the videos that I've asked you guys to watch, but I don't think I've actually done in your class, is just to show that, you know, if we have AV1 is lambda 1 V1, and AV2 is lambda 2 V2, like that, right? Then if we look at P equal to V1 V2, we can calculate that P inverse AP is equal to, well, lambda 1, lambda 2. Right? In other words, and I typically call this thing D for diagonal, right? So this problem 116 example, you can calculate the eigenvalues and eigenvectors. And it is, in fact, diagonalizable, right? How does that help you calculate a to the power n? You guys do have lab this week?
Yes.
All right, I'm
We
wrapping.
have lab
In-
mostly every Thursday.
Dang it. Well, I'll be wrapping up here soon. So, all right, so I was hoping against hope that there was no lab this week, but I was wrong. Okay, so why does this help you calculate a to the n? It's very simple. You can solve this for a. Ha 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 ha. PDP inverse, right? And that might not be that exciting, but notice that a squared is PDP inverse PDP inverse, right? What happens to the middle P and you get P D squared P inverse. How do you calculate D squared? You just square the diagonals. Right? You just square the diagonals. It's really, really easy. So, to calculate, ha ha ha, you bad guy. To calculate a to the n, we do p d to the n, p inverse by essentially the same telescoping of the interior p inverse pairs happens. And so this is straightforward to calculate because d to the n is nothing more than lambda 1 to the n, lambda 2 to the n, right? And then this calculation, P matrix, you can easily calculate P inverse is straightforward. It's, you know, it takes 2 lines, but that is how to calculate a to the n. So the diagonalization of a matrix allows us to do all kinds of calculations that are perhaps non-obvious from another viewpoint. That's the idea. That's 116. All right, well, with that, I must pack up. And then I'm going to try to take 5 minutes to see if I can't find us a better place to do this.
Are the children here all day?
I hope